Hi, everybody. This is David Paul, and welcome to our webinar today on medium pressure UV. Our guest speaker will be from Aquionics, and his name is Dan Shaver. So this is one of the webinars in a three-part series. The first one a couple of weeks ago was on HOD UV, which is also a medium pressure UV, and today is on medium pressure, and then 2 weeks from now we'll have one on low pressure UV. It'll be a 45-minute presentation. It won't be any more than 10 minutes of an intro. Then Dan will give about 35 minutes. Then we'll have 15 minutes for question and answers. So if you have a question, just type it into the question box or chat box, and then we'll cover it at the end when we get to the Q&A session. You'll receive an email right after the webinar with a 3-question survey, and it won't take very long, so please fill that out so we can get some feedback on what you thought about the webinar. We're going to record this presentation. It'll be available on our website next week. You'll also be sent a thank you email in the next day or two, and it'll have a PDF of this presentation. So all the slides that you'll see, you'll get a PDF of that very soon. So just so you know, there is no money that transfers here. Aquionics and David H. Paul Inc. do not have a financial relationship. We just do these webinars because we think it'd be valuable to our clients. So I've been in high-tech water treatment, mainly industrial, for a lot of years. A Master's of Science degree in microbiology, and also reverse osmosis specialist 4 certified by DHP. Dan Shaver has 10 years experience in the water industry and is strategic account manager for Aquionics, and his primary focus is on UV disinfection guidelines and water quality specifications for leading organizations in the food and beverage industry. So I'm just going to do a really brief introduction, and then Dan will give the details. So this is on UV in general. So UV is part of the electromagnetic spectrum. You know, we can see that the wavelength of UV is between 100 and 400 nanometers, that X-rays are a smaller wavelength, so they have more energy, and higher, slower wavelengths are in the visible range, which is what we see. And when we talk about wavelength, we're just talking about from the beginning to the end of the wave, what is that length? So 100 to 400 nanometers would put it in the UV wavelength. So scientists are always looking at, how are we going to make some money off of this electromagnetic spectrum? Well, everybody knows that they found that X-rays are stopped by bone, but aren't stopped by soft tissues. So we go in and we get an X-ray and we get to see the bones inside of our body. Well, when they looked at this UV radiation, they found, hey, we can destroy organic molecules, TOC, total organic carbon, if we can find something that has a wavelength of maybe 170 or so, we would get maximum effectiveness of destroying organic molecules. And we would get maximum destruction of ozone and chlorine if we're about 254, 255 nanometer wavelength. And we could inactivate bacteria if we could get something that was producing UV radiation in, say, 260, 270 wavelength. Well, all right, now they're looking for, how do we find something that will produce the wavelength that we want? Well, if we energize sodium, Na, visible light is produced. That's not what we want. If we energize potassium, K, same thing, visible light. But if we energize mercury, Hg, UV light is produced. So that's why the UV lamps are going to have mercury inside of them. So 2 flavors of UV, low pressure and medium pressure. That's based on the actual pressure inside of the lamp. So for low pressure UV, there are primarily 2 wavelengths produced, 185 nanometer, and that's used for organic destruction, and 254 nanometer wavelength, which is used for bacterial inactivation and ozone or chlorine destruct. So a low pressure lamp produces both 185 nanometer and 254 nanometer, but only about 5% 185 and about 90% 254, and the remainder is just scattered. So you can see that it says mercury and argon. Well, argon is just a carrier gas. It's not actually producing UV. So if you want a 254 nanometer low pressure lamp, then the manufacturer puts a compound into the quartz of the lamp, and that blocks the 185 from coming out. Then you have strictly a 254 nanometer lamp. And that's going to be good for bacterial inactivation, and that's going to be good for ozone or chlorine destruct. If you want to get rid of organics, then you really want 185 nanometer. Well, it's the same lamp, but it doesn't have the dopant in the quartz of the lamp. So you have, again, 5% 185 and 90% 254. But that's going to be good for TOC or organic destruction. But because only 5% of the wavelength coming out is going to be the 185, the 185 nanometer units are going to be much bigger ordinarily. But because you still have the 90% 254 nanometer coming out, an ozone destruct UV unit is also a bacterial inactivation and can destroy ozone or chlorine. Medium pressure, and this is what Dan's going to give you a lot more detail about, it takes more energy, input energy, but puts out a whole lot more output energy. So lots in the UV range, also some in the visible range, as we see here. So about one medium pressure UV lamp is equivalent to about 16 low pressure UV lamps. So just to wrap up, pre-RO, I don't find it to be common in many industries except for pharmaceutical and biotech in the companies that we deal with. So in biotech, pharmaceutical, it's not uncommon to see UV in front of an RO unit for bacterial inactivation and or dechlorination. In several high purity applications, especially semiconductor microelectronics, then we'll see downstream of an RO unit, we'll see the 185 nanometer UV because they want very low TOC levels. So we see here double pass RO, electrodeionization, mixed bed ion exchange. So this is going to be very, pure water, but to get the TOC down extremely low, they put a 185 nanometer UV unit in. It will also, of course, be bacterial inactivation. And then if they want less than 1 part per billion, today's technology, maybe even less than 500 parts per trillion, they use ozone enhanced 185. And the 185 nanometer helps with the TOC in the presence of ozone, gets the TOC very, very low. And because it's also producing 254 nanometer, if it's low pressure, then you get the ozone destruct. And then very common that the two last steps in a super high purity water treatment applications, you have a 254 nanometer to inactivate bacteria, and then an ultrafilter to pick up the bodies and any other particles. So that is just a brief intro, and I'm going to turn it over to Dan now, and he'll give the presentation on Aquionics medium pressure UV.
Very good. Okay, thanks, David. So I've got my slides up here. So some of what I'm going to cover off the start is a little bit of what David covered as well, but I think it's important to have a bit of background on that medium pressure UV before we jump into the application. So real quick, if you haven't heard of Aquionics, we are part of the HALMA organization. The HALMA UV group consists of 3 different UV brands, which you may or may not have heard of. We have Aquionics, Hanovia, and Burson that all make part of that UV group that gives us coverage around the world, with our US head office for the Americas based in Charlotte, and our global headquarters based just outside of London in the UK. So going back to the basics of some of what David covered with the basics of UV disinfection, when you take that mercury vapor lamp and excite it and emit that wavelength of light, it's very close to that peak absorption of what the DNA absorbs of the most common bacteria and virus that are found. And that peak absorption happens around the 260 to 265 nanometer wavelength. So by exposing it to that UVC light, it actually destructs part of that DNA, prevents reproduction, and disinfects your water. So UV is a very effective treatment against some of the known chlorine-resistant organisms like Crypto and Giardia that you've probably heard of. So if we look at when we're actually sizing a UV system, and this goes into the equation of whether we need to look at medium pressure or low pressure and the differences and advantages, we look at something called dose. And that UV dose value is often expressed in millijoules per centimeter squared, which is probably the most common way that you'll see it written. That UV dose equation, very simply, is made up of the amount of UV light that you've got and how long that water is going to be exposed to that UV light. So the intensity can be factored in and affected by a number of different variables. That residence time, or the length of time that that water is going to be exposed to the UV light, is really just a function of your flow rate. So you've got intensity and flow rate that really make up that UV dose equation. Part of that intensity value, it can be affected by a number of different things, not just the kind of lamp that you're using. Some of it has to do with the water quality as well. So a very important factor in understanding that UV dose and how much is going to be effectively delivered to the water. One of the biggest parameters that we look at is something called UV transmittance. And UV transmittance is really just a measure of a percentage of water that's going to penetrate through a sample. So 100% transmittance is going to be like a deionized water that's very pure, nothing in it that is going to scatter or absorb the UV light. And as you get down in scale, whether it's municipal water that has a bit of chlorine residual in it or wastewater, that percentage value will drop. So other things will affect that, that transmittance number, and will also affect the dose equation. We get into looking at things like turbidity. Certain minerals like iron and manganese are going to affect that, the performance of the UV system, and certainly the concentration of suspended solids going through the chamber. So once we understand dose and how we get there, often we need to take a step back and say, well, what is it that we're actually trying to achieve? What organism is it that we're trying to target, or what virus? So that's important when we look at low pressure or medium pressure, to understand what type of lamp we need or how much intensity we need. We might want to know what it is we're actually trying to inactivate. So this chart's really just a representation to show you that there are different dose levels required depending on what it is we're trying to target. So you can see in the example here, and this chart is just really a cut from a chart of several pages of different organisms that have a known dose response. Something like a Legionella is going to take a much lower dose than something like an adenovirus. So there's a big difference there between how much UV would be needed to get the same 3-log activation of each of those organisms. So David mentioned a little bit about the difference between low pressure and medium pressure. So once we know the dose that we need and what kind of application we're looking at, we can make a decision between whether low pressure or medium pressure is the right way to go. There's definitely a time and place for both, and David mentioned that the wavelength output has something to do with that. So a medium pressure lamp is what we consider a polychromatic lamp, outputs many different wavelengths. Low pressure is monochromatic and outputs a single wavelength. Again, there's a time and place for that. There's advantages to both, but I'm going to focus specifically on the medium pressure side of things. So some of the advantages to medium pressure over low pressure, and it's not to say that one is better than the other. As I mentioned, it just depends on the application, and it depends on what performance is required. So medium pressure is going to be great for maybe a higher dose application, treating a higher flow rate or lower water quality, excellent for that. Some of the other advantages on that chart that you see with the medium pressure lamp, you do have a higher intensity, but the trade-off there is you're going to get a little bit shorter life out of a medium pressure lamp. Low pressure is going to have a lower intensity, but a somewhat longer life. Medium pressure, when we talk about the actual footprint, the form factor of a medium pressure system is going to be generally smaller than a low pressure unit. So you get a more compact footprint with a higher intensity light. With that higher intensity light also comes some of that energy transferred into heat. So in a lot of cases with medium pressure, we have to be aware of the heat generation of medium pressure and deal with that, whether it's through recirculation or other means. So there's a couple of examples of what a medium pressure system might look like. So we've got a variety of different form factors there, whether the water is flowing parallel to the lamp, single lamp versions, multiple lamp versions, versions that are cross flow with the water going perpendicular to the lamp. With medium pressure and with any UV lamp, there's going to be some maintenance. So just real quick, I want to look at the maintenance expectations. So a medium pressure lamp is going to have expected life of about 8,000 or 9,000 hours of runtime. So generally once a year, depending on the operating cycle of the UV system and if it's going to be turned off and on, that will also affect the replacement interval of the lamp. The quartz sleeve, those generally need to be replaced every couple of years. The intensity sensor will drift over time. It's going to need some calibration. And also if your system is equipped with a wiper, that wiper will also need to be serviced to make sure that it's operating properly. So jumping into the applications, we're going to talk a little bit about some applications pre-RO, and then we're going to look at a few post-RO. So there would be a typical process map of where you might find UV in, for example, a beverage environment. So we're going to talk a little bit about UV around the pre-treatment side of things, maybe at what would be found at the inlet of a plant, and then we're going to talk a little bit about what would happen after the RO. So right from the beginning of that process, we often have people looking at UV as a way to protect their source water. So everything coming into a plant would go through, first thing would go through the UV, where the UV would essentially act like a firewall to their process. So this is where we'd be disinfecting that source water to ensure that everything beyond that point, they're getting good water quality for everything coming into their plant. And they've protected themselves against any bacteria or contamination events that may have happened outside of the plant that could make their way into the plant. So there's a lot of reasons why a plant might do that. There could be, past issues with water quality being affected if they're on, whether it's a well or a municipal source, but there are, several different factors there why a plant might want to look at that source protection. So some things to ask yourself if that might be an application for you. You might want to look at what other water treatment barriers are present at the intake of the plant. Have there ever been any source water issues in your area? How often do you test for bacteria coming into your plant? Things like that might give you a good indication of whether UV as a firewall might be a good application. So a little further up the line, we get into pre-treatment. So here, where there might be pre-treatment such as carbon or other ultrafiltration, this is an excellent spot to combine medium pressure UV. So carbon's often in place to, say, remove chlorine or other contaminants. Filtration's great, but it's a great spot to breed organisms where bacteria could be found in those carbon tanks. So having a medium pressure UV system after the carbon is going to be an excellent protection for the rest of the process, especially as you get up into the RO process further down the line. So that might be something to consider. If there are pre-treatment processes in place, you may want to look at what those are and what kind of protection is in place for disinfection, along with that filter process to make sure that you're not getting any other contamination down the line. So moving on to the next stage, we have looking at using UV ahead of an RO. So some of the reasons you might look at that, whether it's for disinfection, as we've been talking about all along, or UV can actually be used to destruct chlorine ahead of an RO as well. So a couple different purposes there that you might want to consider. So a lot of people are familiar with disinfection, obviously, with UV, but we also focus on talking to customers about the destruction of free chlorine. with medium pressure UV. There's been some work done on medium pressure versus low pressure UV and how that affects the free chlorine in the water source. And it has been found that because of a little bit broader spectrum of the peak absorption of those species of chlorine, medium pressure is proven to be a very excellent treatment method to reduce that chlorine. It should be noted that the dose required to actually destruct chlorine is significantly higher than what would be required for disinfection. It can be up to 20-25 times the amount of dose depending on the water quality and depending on the amount of TOC in the water, but medium pressure is definitely an excellent option if you wanted to consider it as an alternative for dechlorination in your process. So some things to ask you is yourself if dechlorination might be a good application for you. You might want to look at what your current methods of dechlor would be, whether it's carbon, whether it's sodium metabisulfite. Maybe UV could be a good alternative to either of those, given that it's a chemical-free option. If carbon's being used, you might want to look at your maintenance associated with that, and if UV could be a good alternative to relieve your facility of some of those costs. Same thing with the sodium metabisulfite, looking at what you're spending on chemicals and the maintenance involved there. Maybe UV could be a good replacement. So by looking at UV as a dechlor, you're also getting the added benefit of, because of the higher dose of UV required to destruct the chlorine, you're also getting the disinfection included in that because you're already applying a considerably higher dose. So looking for a little bit further down the line, once everything's gone through filtration, UV, RO, there are some applications further on that we see medium pressure as a good fit for. One of them is in the dairy industry, where we look at the FDA's pasteurized milk ordinance. So the PMO does indicate that UV for certain applications is suitable to create pasteurized equivalent water according to their requirements. So we see this in dairies for use as product push water, reclaimed cow water, CIP applications, other rinse applications. So as long as the UV is meeting all of the technical requirements of the PMO, it can be a great option for plants that are looking to produce that pasteurized equivalent water. So a few questions to ask yourself if you were a dairy and you were considering UV, after your RO and you had this purified water that you wanted to look at and you needed to create pasteurized equivalent water. Do you have pasteurized water in place already? And is it something that you could use UV as an on-demand solution versus pasteurizing it and holding it in a tank? This could maybe free up some of that storage and add some production efficiency to your process. And if you are using pasteurization, perhaps the HTST equipment is due for replacement and you're looking for an alternative there. So the medium pressure UV could be an excellent option because it does tend to meet that high dose that's required by the FDA's PMO, which is 120 millijoules. Further down the line, David mentioned a little bit about ozone earlier. So we do come across from time to time customers looking to eliminate ozone from their water source. And it has been proven that medium pressure is an excellent way to reduce that if ozone removal is something that you're looking at. So there is a good relationship between a medium pressure dose and the reduction of ozone. So you see from the chart there that generally we would size a medium pressure system for about an average dose of 120 millijoules to get a 1 log reduction of ozone. So it can be done, and we do see this from time to time with customers. So just to kind of sum up the applications there, take you through that chart again. UV from the beginning, when we're looking at applications before the RO system, we're looking at source water protection. We're looking at putting medium pressure after a carbon filtration bed, where we'd be looking at controlling the bacteria that comes off that to eliminate any potential biofouling going through the rest of the process. Directly ahead of the RO, we'd be looking at reducing biofilm and also potentially looking at dechlorination before the RO to eliminate that from the process. Then further down the line, once everything's gone through the RO, there are a lot of other stages after looking at this specific chart, maybe in a beverage process, looking at the deaeration tanks or other processes down the line that could use UV for disinfection, even after it's already gone through the initial stages of treatment. That's all I have for now, so I'll turn it back over to the organizers.
Thank you, Dan. And we have a lot of time now for questions. So if you haven't already filled out in the chat box or question box, if you haven't put a question in, please put your question in now. And now Dan will read the questions. We'll do them one at a time and then give the answer.
All right, so the question here is, since UV lamps generate both 185 and 254 nanometer, why would we add dopant to eliminate the 185 wavelengths? Is there some disadvantage of having 185 energy in some applications? Yeah, so our, the experience that I've got with the lamps that we use, certainly that we are focused on using only the wavelengths that are really absorbed by bacteria and virus. So making it more efficient for the system to only provide the disinfection. So that's really what we've been focused on, is just focusing on that band of UV that's used for disinfection. So another question's come in, would UV help to destruct chloramines ahead of RO? So the research that we've got, I do have access to a white paper that we did on the destruction of chlorine, where it was focused on just the reduction of free chlorine in the water. So it's not something that we come across too often, other than maybe in the aquatics industry. But all of our research really is focused around the reduction of free chlorine. So another question's come in with a PMO application needs some devices to reach the rule, like flow meters, control flow valves. Does Aquionics have them? So those instruments are not something that we provide directly, but quite often on a PMO project, we would be also working with a third-party integrator that would be able to provide those things, whether it's a UV transmittance monitor, flow meter, control valves. All that peripheral equipment is something that would be integrated in as third-party equipment. We would just essentially provide the UV system. Another question has come in, how do you ensure no mercury is entering the product water during a lamp breakage during service or maintenance? So again, we definitely do focus on just the UV system, but when it comes to the actual installation and the integration of other components in, from time to time we do see people put in other peripheral equipment, whether it's strainers or filters or other control mechanisms to make sure that if there was a break that they could divert the flow. Those types of processes are often left to the third party, where it's not something that we would provide, but certainly there are methods to actually get around that to make sure that if there was a break, that you could signal that there was a break, whether it's an alarm from our UV system saying that something happened, so that you could divert flow or take appropriate measures to make sure that none of that contaminated water was getting into your product. Another question here, there's a debate about the position of polishing filters before or after UV lamps. What is your recommendation? Yeah, so if we're talking about filtration before or after UV, I think there's benefit to both. I think sometimes it just depends on the actual process, whether it's putting UV for control of any bacteria that could come off of the filters, then certainly there's a benefit there. In theory, you could have the UV ahead of it as well to eliminate any bacteria going in there. Our recommendation's always been to put the UV as close to point of use as possible. So if you have a known issue with bacteria coming off the filter or further down the line from the filter, it'd be a good idea to put it as close as you can to where you're going to be using the water. If you know that based on source water or any of the water coming through that pretreatment process, if you have known issues there, and you wanted to lessen the bioburden upstream of the filter, then certainly that'd be a good practice to put it in ahead of the UV or ahead of the filters as well. So another question here, what considerations must be made for flow through the lamps? Straight pipe lengths, would turbulent flow be advantageous? So the recommendations for installation before and after, if we're talking about when we get into validated systems that follow US EPA guidelines, the EPA does have some instruction in their UV-DGM, the guidance manual for UV, that indicates a certain length of pipe upstream and downstream of the UV to make sure that any kind of validated performance is not affected. So that certainly would need to be taken into consideration, and that's going to change depending on the system that we're looking at. So often it is a multiple of the diameter of the flange on the UV system itself. So the larger the system, the longer that straight run of pipe before and after the UV system are going to be made. So another question, can medium pressure UV destroy organic molecules? So yes, they can. Reduction of TOC is not actually an application that we focus too much on. We do have some past experience with it, but certainly not. It's not something that we're currently sizing for. Another question here, on average, what percentage increases the life of the membranes using UV in pre-RO? So that's something that that we've been working on. The theory is that it would essentially, by whether it's reducing the bioburden and reducing the burden on a CIP system, or doing a dechlorination application where you would be preserving the life of that membrane. I haven't actually seen any numbers as far as months or years or any kind of time frame on what that life increase would do, but it's certainly the theory and the science behind it is definitely there. But so another question here, can you use UV for chloramine reduction? We had this question a little earlier. All of our application research and everything in the sizing is based on just the reduction of free chlorine. Can you use this for THM removal or reduction? So again, when we look at THM removal or reduction, it's not really an application that we have been focusing on. We haven't got the research on that, so it's not something that we're specifically focused on right now that we'd be able to provide support for. So another question here, what do you do about the 1 sensor per lamp rule for the PMO? So with our medium pressure systems, when it's a validated system, they do have 1 sensor per lamp as required by the EPA. So as long as we're looking at a US EPA validated system, we are able to meet the 1 sensor per lamp rule that is written out in the PMO.
While we're waiting for some more questions, this is David Paul. I thought I would respond to question 1 and 2. Question 1 was, why would you want to remove 185 nanometer from put the dopant into the lamp quartz so that the 185 doesn't come out? Now, again, this is a low pressure application when we were talking about that. And Dan's been talking about medium pressure. So whenever you use a 185 nanometer, so again, a low pressure lamp, you are destroying organics. And the organic molecules, if they were destroyed totally, would go back to CO2 plus water. And CO2 plus water combines to form carbonic acid and bicarbonate ions and carbonate ions. And this then will increase the conductivity. The organic molecules themselves may or may not be ionic, so they may or may not influence the conductivity. But when you whack organics with 185 nanometer, you will get a conductivity increase. So in high purity water applications, whenever you use a 185 nanometer lamp, then downstream of that, you have to put a polishing mix bed in so that you can get your conductivities back down. You remove the ions that the 185 nanometer UV produced. So that's why when you want organic reduction, then you have a 185 nanometer lamp. If you want to disinfect only, and you don't want to change the conductivity, you don't want to get rid of organic molecules, that's when you put the dopant in so that you don't have the 185 nanometer coming out. The second question on chloramines pre-RO. So for low pressure lamps, yes, there's indication that you can, reduce the chloramines, but in most applications, when you're talking about pre-RO, you're trying to protect the RO unit from free chlorine, not so much the chloramines, the combined chlorine. So for example, an RO membrane may have 1,000 ppm hours of tolerance to free chlorine. So 1,000 ppm hours means 1 ppm for 1,000 hours, or you multiply the dose times the time, and it comes out to 1,000 ppm hours. Whereas for chloramines, the RO membrane may have 100,000 ppm hours of tolerance. So chloramines do not have the same oxidative power as free chlorine. So if you have chloramines going into an RO membrane, unless you have iron laying on the membrane, is not going to be an issue. It probably, at least for the RO membrane, it may be an issue downstream, but not for the RO membrane. So I personally have never seen an application where using UV pre-RO to try to get rid of the chloramines. So I wanted to just reply to questions 1 and 2. Now we'll see if there's any more questions that have come in.
So we had one more question come in here. Do both technologies work equally well in hot water systems? So, certainly both, I'm assuming we're talking about here low pressure versus medium pressure. So as I mentioned earlier, that with a medium pressure lamp, you've got a significant amount of heat generation over a low pressure lamp. So that is going to be a factor where we just need to make sure that we understand the application and make sure that we understand that we're operating within the thermal tolerance of what we would allow, depending on what type of lamp we're actually using. Another question here, is it a myth that if water passes 2 times through UV lamps, the second one could actually reactivate microorganisms? So I have not seen anything that would show that reactivation happens. And that's not something that I'm familiar with. So another question that came in here, does medium pressure UV output 185 nanometer? I think as David said, we'd be dealing with a low pressure application there where the band of medium pressure is significantly higher than that. And that looks to be the last question. So I think that's all for now.
All right, well, thank you, Dan. Appreciate all the answers to the questions. And if you have any questions that weren't covered, then just send Dan an email so he can give you a reply. So it's unusual. Thank you, Dan, for your relatively brief presentation, because this is, I think, the first time that we have actually ever been able to cover all of the questions that came up. So just for your information, we do have a 3-day high purity water treatment classroom seminar that includes UV. We also have lots and lots of training. So if you have any water treatment training needs, please give us a call. So thank you so much for attending. You'll receive an email after you get out of this webinar. It has 3 questions on it. Please reply to it. It won't take any time at all. So thanks so much, and we'll see you at the next UV webinar in a couple of weeks. Bye-bye.